dogs. Okay, so the classic lab that we did, like I talked about before, is to hand students hot dogs and say, find the specific heat of the hot dog. And for about a week, the students look at you like you're insane, and then like it dawns on them of how to do this, and we eat a bunch of hot dogs, and they get a cool answer. So the way we actually go about doing this in the lab, and we'll kind of like just talk through it, is everything starts with a styrofoam cup. This styrofoam cup is going to act as a calorimeter, okay? This calorimeter is what is causing our closed and isolated system. Now, truth be told, whenever we do this in a high school lab, we're not very good at sealing our calorimeters, so a bunch of heat ends up escaping, and it causes errors to occur in our data. But we're going to propose that we're great scientists and that our calorimeters are perfect in every way, and we don't have to worry about them, okay? Now, one way of doing this entire lab, is to take a styrofoam cup. And styrofoam works really well because it's like a nice insulator. It's got a pretty nice calorimeter constant or a specific heat. So we know for the calorimeter, it has a mass of 10 grams, and it has a specific heat or a calorimeter constant of 1.4 joules per gram Celsius. Okay, so that's what we know about our calorimeter there. We also know that there's 50 grams of water inside the calorimeter. So whoop. Here's some water. And if you think this lab sounds crazy of just handing someone a hot dog and saying, find the specific heat, it's actually a lab some colleges make their students do. So this is a great one. Now we know that this system here, the calorimeter, we'll close it off, the styrofoam cup with the water in it, it's at a temperature of 23 degrees Celsius, okay? So initially in this problem, we've got the styrofoam, we've got the water, and our temperature is 23 degrees Celsius. Now what we're going to do is we're going to take a hot dog. Like its temperature is warm, so it is hot, and it is a hot dog. So it's a hot dog. Here it is, a little hot dog. And we are going to drop it into the water. And we're going to maybe not just drop the hot dog into the water. Maybe it's a better idea to like puree the hot dog and heat it up and then drop it in so it mixes better. But like that's a laboratory procedure issue, not really a theoretical, let's just talk about calorimetry issue. So if you are doing this lab, puree your hot dog, people. Chop it up into fine bits whenever you heat it. Okay, it'll help you out. But we know the temperature of this hot dog. We know the temperature of the hot dog is initially 80 degrees Celsius, and we know the mass of the hot dog. The mass of the hot dog is 30 grams. Okay, so we know this information about our hot dog. And we know information about our water / calorimeter. What we'd like to figure out here is if we took a temperature probe and we stuck a temperature probe into this system, after some time, the final temperature of the system is 36 degrees Celsius. So the final temperature, or the equilibrium temperature, where everything's the same temperature, is 36 degrees Celsius. This means that our hot dog cooled down, it sent off some of its heat energy into the water and into the cup, and the cup, which was colder than the hot dog, took that heat upon it and heated up by some amount. So we got everything to equal this equilibrium temperature at the end. What we would just like to know is, what is that specific heat of the hot dog, okay? How much energy does it take to increase a hot dog's temperature by 1 degree per mass of the hot dog, right? So this is how we set this problem up. We just add up all of the delta Q's. We know that this problem is just going to be a change in heat, or change in heat energy from the styrofoam, and it's going to be a change in energy of the water, and it's going to be a change in energy from the dog. Our water is going to heat up, our styrofoam is going to heat up, our hot dog is going to cool down. If you add all of the changes in energy together, this has to equal 0 because this is a conserved system. It's a closed, isolated system. All the energy is conserved here. So everything added up has to equal 0. So at this point in time, we just need to use our ideas of calorimeters and calorimetry to plug in some values here. And this gets a little bit annoying just because there's so many numbers, but it's not a crazy thing to do. Let's write it out analytically first, so just with variables, and we'll see what we're talking about. So for the styrofoam, we're going to have the mass of the styrofoam. We're going to have, or we can call this the calorimeter. Maybe it's best if we call it the calorimeter itself. Let's call it cal. So we're going to have the mass of the calorimeter, the specific heat of the calorimeter, and then there's going to be a delta T here. Now remember, delta T is always a final minus initial. So when we do final minus initial here, well, what do we have for the final temperature? Well, we said that the equilibrium temperature was 36. So either way, it's going to be the equilibrium temperature minus the initial temperature, which we knew was 23. So there's Ti. Okay. Now let's do this for the water. It's going to be plus the mass of the H2O times the specific heat of the H2O. That's that 4.186 that we need so often. And then it's going to be the equilibrium temperature minus Ti. And then for the hot dog, plus the mass of the dog, the specific heat of the dog, which this is actually what we're looking for here. And then multiplied by the equilibrium temperature minus the initial temperature for the hot dog. And this all equals, well, what we know to be 0 because the energy is conserved. So that's a large equation there, but we happen to know like all of these numbers. We know the mass of the calorimeter. We know the specific heat of the calorimeter. We know the final temperature of 36. We know the initial temperature of the calorimeter, 23. We know the mass of the water. We know the specific heat of water. Finals 36, initials 23. We know the mass of the dog. We know the final temperature of the dog is 36, and we know the initial temp is 80, which means that we know every single number here except the one we're looking for. So there's a lot going on here, but once we get this set up analytically, it is just a matter of punching in values and calling it a day. So let's just write this out with all of our numbers here, and then just be careful about that. So our calorimeter itself, and I'm going to keep everything in terms of grams because that's how I like my specific heats. So our mass of the calorimeter is 10 grams. Specific heat of our styrofoam calorimeter is 1.4 joules per gram Celsius. And then the equilibrium temperature is that 36 degrees minus the initial temperature of 23 degrees. That's going to be 13. So if you wanted to write 13 there, that's not an issue, but you know, we write everything. And then plus the mass of the water, well, we put 50 grams of water in it. That's also 50 milliliters. 1 milliliter is a gram of water. So there's our 50 grams. We know the specific heat of water is 4.186. Don't believe Google. If you Google it, it'll say 4.182 joules per gram Celsius. And then our temperature difference is once again going to be the 36 minus 23 because it did the same thing as the calorimeter. For our hot dog, and as you see, this is starting to take up more and more space as we write everything out. That's the one annoying thing about these problems. We know the mass of the dog here. That was given to us in the problem. It was 30 grams. You know, just we took a little bit of a hot dog, 30 grams worth. We're looking for the calorimeter constant, or the specific heat, excuse me, of the hot dog. And we know its final temperature was 36 degrees, but the initial was 80. And all of this is equal to 0. Yay! At this point, you got to pull this sucker out, and we just got to crank through some numbers. So 10 times 1.4 is 14. 14 times 13 from the 36 minus 23. All of this here gives us 182. And these units are going to be in terms of joules, because our grams and grams cancel out, and these are all in degrees Celsius, so the degrees Celsius cancel out. So 182 joules plus 50 times 4.186 times 13, 2,720. There's a 0.9 there, but let's just make it 21. I don't want to write anymore. And then plus, and then I'm going to have a CD here because that's the hot dog. So let's just do 30 times the 36 minus 80. So we're actually going to get a negative 1320 CD. And that negative is important because this negative implies that the hot dog lost energy. The hot dog was losing energy here. And that makes sense because, you know, it was giving its energy into the water, into the styrofoam around it. It was cooling down. And this all equals 0. At this point, this is pretty much straightforward math. We are going to, it doesn't matter if you put these together first and then move them over, or if you move them over individually and put them together. But these two are like terms. They're numbers. We can put them together and shove them to the other side. So 2721 plus 182 is 2903. We move it over to the other side. It becomes negative. So we get negative 1320 times CD equals negative 2903 joules. And then, if this computer would work, then the last part, we see it. We divide by the negative 1320, divide by the negative 1320. The units of the 1320 were grams, degrees Celsius. So 2903 divided by 1320 gives us a specific heat of the hot dog of equaling 2.2 joules per gram degrees Celsius. And that's actually a pretty good value for a hot dog if you got something around that. Students in the past have gotten anywhere between like 1.8-ish to maybe 3-ish. But hot dogs can be a little different when you're actually doing them in the lab. Some of them are natural cased. Some of them have cheese on the inside. Some of them made are chicken, pork, beef, who knows what. I think one year we had tofu dogs, which kind of messed everything up. But that is how we go through a problem like this. We take a look at what we have in the system, what we are mixing together. We're assuming we mix it well. We look at all the changes in the heat that we could have, all the changes in heat energy. This is very important right here. We list them out, MC delta T, MC delta T, MC delta T. We look for the unknown variable, and then it's just algebra at that point, where we just put numbers together and we find our final answer, the specific heat of a hot dog. So very cool thing here, very fun lab. You can do this with all sorts of different objects, assuming that you have a nice closed and isolated system. If you let a bunch of heat accidentally escape, you're going to get a very, very different answer than what we have here. But this was the first kind of example we've seen for calorimetry, the hot dog lab setup. And this one is finished. We'll be doing some more calorimetry stuff, looking at some other examples as we continue on in this. But for right now, adios, and y'all take it easy.